It turns out the numbers, those simple numbers you learned as a kid, are games. Not just in a vague or metaphorical sense. Actually, on the contrary, reduced number games are determined and losslessly compressible. They are orderly compositions, a special class of relativistic patterns, relationships defined by an exchange of predictable information, even when one or all players involved do nothing. What does all of that really mean? Well, I'll show you. While fantastically reliable, the numbers not really great fun as games. The label of a win or loss will of course vary depending on some adopted rule set, but the structure of a reduced number game itself is invariant, kind of like a pruned tree. In fact, people tend to stop playing a game when it turns into a number, when there are no more difference-making choices for either player left to make, at which point we just tally up to see who won. In this primer, we will walk through the simplest details of numbers as games. First, I'll quickly mention the main thrust of the Surreal Physics channel will continue to be the more intermediate level content, delivered in a storyline over many episodes, in a swirl of art and context. I encourage your further study on any material mentioned to really get to know it, which usually means going through some examples, if not trying to apply it in some way. Cross-references and getting others' perspectives are highly encouraged. But I've come around to your feedback that more primer material on surreal construction would be really useful. Please continue to send your thoughts and questions in the comments. Great books, other writing, and more resources on combinatorial games and their surreal numbers are linked in the description. These approaches deserve a lot more attention than they get in any context, including academia. As a well-trained physicist, I'd never heard of them, but I found them to be so incredibly rich, enriching, expressive, and even enlightening, not only for physics, the details of which will keep unfolding in the main episodes. In the meantime, here's the start of some simpler explanation of the surreals. To make any surreal number, you need what is necessary for any combinatorial game, at least two sets, what we'll call the left player's options and the right player's options. These two sets of moves will compose for us a game. At first, we're just going to focus on some simple games that appear as numbers. We can compose games with more than two players, of course, but we'll be sticking with this minimum of two players for now. To kick things off, there are no options. Each player has nothing to play. This game ends as it begins, with no moves, so we call it 0, or as you'll see, the origin from which the rest of the numbers will bloom. But now, by constructing 0, this minimal start to the numbers, we have an option for either player to potentially move to, namely, play to 0. One possible game we can make now would be to give this only known move to the left player. So that means the left set now includes this play to 0 option, always, along with the implicit empty set. That's a game configuration where right has absolutely nothing to do but exist. Poor right. Left can move to 0, but from what direction and how? Well, we can't say much about that yet. With perhaps unfair sympathies in left, we'll call this game 1, as in positive 1, a unit by which to measure the rest. But with at least two sides to any game, there is an automatic symmetry to explore here, turning out to imbue this fascinating proper class with so much surprising structure, non-trivial in the math lingo. When we conversely give right the only move, left now has no options. And how does it feel now, left? And now here we know, -1. Is this move of the so-called right players really the direct opposite of left's non-existent move? Well, that may not make any sense if we isolate the game -1 without any other context, but in the fuller understanding of this class, abstractly at least, yes. Possibly even in a physical sense, it's the opposite as well, to the extent that substrate carries information. At least for now, this is just a matter of definition, that right's move is definitively the opposite of left's. So if we called left's move +1, then its negation we'll call -1. But this is so abstract. Let's look at some simple yet different games to suggest how this same formalization generalizes in many contexts. Some classics of combinatorial game theory are Hackenbush and domineering. Charming, yes, I know. Various versions of both are known, but we'll look at the version of Hackenbush where left can chop solid or blue segments, right can chop open or red segments, and these striped green segments can be chopped by either player. Instead of segments, let's call these edges, as in the graph lingo, which as you see are undirected in this game. Thus, here's +1, which only left can, nothing left, and -1 for right. Very satisfying. I should have mentioned that the ground here is very suggestively 0 for us in this game, empty of moves for both players, and also that any edges no longer connected to the ground are also effectively chopped away. To jump ahead, you might already get an intuitive sense from this how -1 negates +1 and vice versa for any number, as well as how 1 minus 1 or n plus -n equals 0. Domineering is a simple game of flipped over dominoes, where left places dominoes only vertically and right places them only horizontally. Players alternate, simply trying to cover a gridded board where squares are only half the area of a domino, but they may not overlap or hang dominoes off the board. So totally different instantiation of a game than Hack and Bush, creating different structures, but within those we will also find the numbers. And let's just look at +1. And -1, blop. But look, this is also 1, and this is still -1 until boom, -2. Again, the surreals are not just one set. Remember, we need at least 2 sets to compose, and this is part of the reason we call them a proper class, because they construct unambiguous definitions of objects, collections of sets, no one set alone, and what we keep calling compositions. Let's see more properties of these compositions before we get back around to justifying why we are doing any of this in the first place. It's at least as complicated as asking why we play games. But whoa, what was all of that? Don't panic. We're getting there. By the end of this video, we'll have walked through a number of examples, especially with positive and -1/2, not just the simplest integers like these guys. More slowly here with Hack and Bush, we just built +1 and -1. If we build them up together in a game, left can only play to -1, or if instead right goes first, can only play to +1. So composed, they basically cancel each other out, as we see when we play them down to 0. Whoever makes the second move evens the unital score, if we're keeping track. Many more examples are coming your way, but first I'm going to immerse you in some game imagery, while further motivating their general properties. What makes us really care about the surreals? At first, some games, or their representations you'll see animated, won't be fully explained, so that you may pause the videos when questions arise in your mind about how this all works. And I really encourage you to puzzle over it at first. This effort may even be necessary to help ready your mind by the time we get to the more detailed walkthroughs later. Maybe if we all grew up learning numbers through games in surreal composition, they'd feel as easy as they are simple, but I find them not easy. You can see the perspectives of the players as frames of reference, which maybe doesn't sound as fun, but if you think about physics at all, it may help you connect all this game business to relativity. Note how we label what emerges from these compositions, alternating between the 2 frames of reference. Even though the full structure of this game is a collection of frames, to read the structure we must put a hat on, so to speak. One player's or the other's, maybe even one and then the other, but always assuming an identity at any one given time. But what would it mean to wear both of the players' hats at the same time in a game? Pretty absurd, right? The game, in any sense it might make, kind of melts away, doesn't it? Well, what about all those one-player games? Well, think about those. There is always something you are playing against, whether the person who came up with what you're puzzling through, or even some mindless mechanism that someone configured for your game, like a shuffled deck of cards or an algorithm. What's playing against you in real time is not necessarily conscious, but usually some brain power went into the most fun games at some point. But here we may start to imagine a whole gamut of player types, not just who or what you usually consider. Composition reflects both frames with equal importance, even if they don't have the same play options in games generally. While our naming convention implicitly prefers left in a sense as positive, we generally prefer no frame, meaning everything left could potentially do, right could also potentially do, and their moves have equal importance as we quantify what is going on. One is not more fundamental than the other in some universal hierarchy of structural framing or viewpoints. There is this directional ordering that we've named. the underlying structure of which is universal. But we could have just as easily named positive with the opposite convention, from right's way to play down instead of left's. Negative starts to seem like right's positive, but not independently striking out, rather importantly also undoing left's positive, and left undoes right's positive. But either way, once we lock in a naming convention, there is only one sense of direction for order, no matter if we call it positive or negative, lefts or rights. Without forgetting what we do with our names and definitions, we'll stick to the standard convention that left moves positively to keep this as simple as possible. I mean, it's complicated enough as it is. Just keep in mind that this matter of relative perspectives in opposition, which are not independent, perspectives we can even mentally jump between, is a key generator of symmetry that will eventually generate all manners of group structures for us from the numbers and games. All from this relatively simple start, which, getting back to, again, as you see with the specific examples of positive one and negative one, options won't necessarily be so fair in any given particular game. And as you'll see more and more, games give way to other games, which themselves could be compositions of many games, possibly with more than one option for players to choose from, until its end is reached. For positive and negative one, there are no decisions, just the play of one side to zero. Once either player plays to zero, we are back to where we started, the end game, which is also the origin of this game, uniquely where both players are out of moves. There is actually one more composition to make from the zero option alone. Did it cross your mind? Yes, zero on both sides, which means whoever plays first is the one that gets to move to zero, at which point everyone is yet again out of options. Here it is in Hackenbush, yes, the green segments, and domineering. This game is not a number, which I better go ahead and formally define. The game left/right is a number if and only if no member of the left set is greater than or equal to any member of the right. In one or negative one, the empty set on the one side definitively contains nothing to compare to zero on the other side, so the definition of order holds. But in 0/0, or the game better known as star, we better recognize that 0 is equal to 0, which means the left set's only option is greater than or equal to the right side's only option, which, according to our definition, means this game is not a number. And this makes sense when we think about it. Star is sufficiently more like a game we are typically familiar with than these numbers, 1 and -1, which are rather boring and predictable as games. In any number, no matter who plays first or what of their options they play, we know what the outcome will be. That is their point, so to speak. It's what this definition does for us, what makes a number special in our eyes from any other game that we may define in any other way. Deterministic outcomes are a pretty useful property, assuming some rule of winning that even means we instantly know who will win, whatever that means in a given situation. Actually, as soon as we determine the sign of a number, we know who will win. The value is simply how far ahead the winner is in these unital moves defined by 1. While not a good assumption generally, just assume for now what combinatorial game folks call normal play, which is that the last player to successfully move wins. This further defines what the games 0 and star mean under normal play. But even without this definition of winning, a very similar structure of exchange or relationship plays out in a number game regardless, no matter if we see it as a win or loss for either player. This may give you a new framing of something you probably already knew, that by finding the reliable numbers in a given system, those structures will be the most useful in helping us achieve some accurate and reliable predictions. General games, on the other hand, which star gives us a hint to, are not so cleanly predictable. We may need to know who moves first to predict their outcome. Game theorists still call this deterministic, as the structure is known as soon as the game kicks off, as long as you know who the first player will be, and that probabilistically the outcomes can be combined to give an average value to a game even before we know who starts. But you might recognize this is that same annoying kind of determinism that we talk about in quantum mechanics, where you can't actually predict how any particular game is going to go. But it's not that weird or unclassical, we just need to know who moves next. However, this averaged shape of determinism all falls apart once there are decisions to make for either player on their given turn. To then make any determinations worth their salt, we must then know the rule set, what winning means, and presume the players play by some definition of so-called rationality, even dangerously our own implicit definition of rationality. Predictions will probably still be uncertain in the best circumstances, but bounded by known limits, depending on how fully the game reflects a system of exchange. Outcomes will be correlated. Again, not weirdly, just part of the game. While the assumptions about rationality in particular can hold in some special situations, generally these assumptions are not great. For instance, when we're thinking about the simplest systems or entities possible, which may be free to move in playful entanglements, but not necessarily have any capacity to decide how to move in them. Suddenly, a rich causal structure is visible within games that makes room for true free choice along with determinism, bounded by limitations for what is possible, but not necessarily determined. We could call them partially determined, but they're not random, no matter how many times we throw the dice. To get back to a point from earlier, numbers like integers and rationals come from what are known as Partisan games, meaning that the players don't necessarily have the same sets of moves. Otherwise, when the game can only give way to the same moves for all players, it's called impartial. The impartial games actually create structures reminiscent of numbers called nimbers, named after the quintessential impartial game of nim, which was actually probably called all kinds of things over the course of history. But it's where players alternate taking tokens or snacks from any number of piles or stacks. But we'll need to leave these fascinating impartial structures dwelling within the general games for another video. Star is actually the first of the numbers. Taking a step back, you can see how the study of combinatorial games essentially asks, what quantifiable values may be produced when two or more perspectives meet, in any possible sense, where they might engage in an exchange of information, or something. Actually, beyond quantifying values, in time I hope you see how games allow us to qualify values of relationship too, but in perhaps clearer ways than natural language usually give us, and in ways that work for things without what we tend to think of as natural language, as natural as these little values are. More about Star and the other non-number games flowing from Surreal construction will come in none other than episode Star. That's also when we'll get into this tricky but important business of what it means to win, what those assumptions do to a game, let alone its players. But for now, that is all an unnecessary complication for the proper class of no, a fitting shorthand for the surreal numbers, given their apophatic definition, meaning we come to understand them through negation. To reiterate, no member of the left is greater than or equal to the right. Some have alternatively defined the surreals in the positive definite sense, meaning that members of left are less than rights. But this creates some interesting problems, and as we'll see in episode 2, departing from Conway's original definition is quite possibly wholly unnecessary to a constructionist positive logical bias. That probably makes no sense right now, but it's impossible to avoid these complexities in life. More in episode 2. Speaking of 2, again, so far we've had 2 effective steps in time. To 0 in day 0 and to 1, -1 and star on day 1. We're going to keep tracking time like this in what are called birthdays, always a positive measure. You can think of these steps as a measure of dependency distance from our origin number. What will it take to build up or play down? We can think of birthdays as causal structures lying at the heart of the numbers we may build out in more than one direction, but to my simple eyes, birthdays are pretty clearly time, mathematical time. Maybe it's even the time we find in physical space. For a complicated structure, it might be hard to tell its temporal dependency measure. For the simplest integer-like numbers, it's just a matter of counting from one of the 2 perspectives alone. How useful. Counts. Getting along to day 2, we of course make the integers 2 and -2, but also 1/2 and -1/2. Let's check out this region of a domineering board. Left has two choices: to move to 0, which is the end game even with 2 half regions left, no full domino can fit in anywhere. Or left can move to -1, very kindly leaving right space for their domino. If right goes first, that turns out to be the only move they can make. So overall, a little calculation shows that left had an advantage, 1/1/2 of a move. And that is precisely the formal value of this game, the number 1/2. Now, you may have noticed I kept specifying reduced numbers in the intro to this video, because you'll note here now with fractions, and you'll find this curiously with all rational numbers, choices start to matter a little bit more than they did with the integers. Conway calls left's two choices stupid or sensible, but his classical context was humans playing games. Obviously, it depends on the rules and the players. What if we melt away all of that? What if the frames have no idea what they are playing for because they have no ideas in the first place? With players who don't know or care about winning, this game on average still has the value 1/2, but the probabilistic distribution of results from playing this game over and over will look a little different. If left picks either of their choices moving first with even probability, then the more we play, the cleaner value of 1/2 we get in the average. What's extra unique and very cool about 1/2 that we have a lot more to say about as Surreal Physics unfolds is how symmetric it is. Look how changing this assumption about mindful play simply reflects the structure. And the negative values of this game show a very similar involution. But say there was something about our playing or the game itself that forced us to avoid what are known as the dominated options. Or maybe we have the wherewithal and goals to predictably choose them. For left here in the game of 1/2, that means playing invariably to 0 rather than -1. Now, check out this game of hack and bush. No choice exists for either player, so we can't play the same game with assumptions that we did with domineering, at least not in this particular example. But this game clearly still has the value 1/2, especially as we look at the sum of games. It takes 2 copies of 1/2 to balance a game of -1. If this 1/2 game was any other value, then this game equation wouldn't work out. But it does. It turns out we can add any games like this in the way you'd expect as you learned to add numbers as a kid. When we find a balance and moves between the players, we have found a 0 position, and the second mover will win in regular play. A major property of general games is that the negative of a game added to the original is a 0 game. Note both 0 and star are their own negatives. Finding equilibriums and systems is perhaps something you think a great deal about, but this is just the beginning of what operations and equilibrium means in games. Regarding those reduced games, whatever that forcing function was, or self-directed preference, perhaps intelligence, whatever it was that predictably reduced our game, it simplified it without changing the simplest notion of its value. Formally, the dominated options are those that are comparably less than some other option in left, and its opposite for right, meaning that if an option is comparably greater than it, it is dominated in right, given that right seeks to maximize negativeness of outcomes. But remember, that's a classical assumption, not generally the case. Technically, reduced games also excise what are known as reversible options, but we'll get to that formality a bit later. A reduced game can be simpler to represent, and you can imagine all kinds of ways this might happen in nature or systems more generally, in different projective, compressive, or compactive ways. We're going to get into this more in episode 1, when we finally get there after episodes I and star, but 1/2 makes simply clear for the first time how Conway employs what are known as Dedekind cuts, especially intuitive for rational numbers. 1/2 is said to be the simplest number between 0 and 1. But what does simplest really mean? Is it the same as that reduced concept we were just talking about? It certainly seems related. Well, think about what would happen if we started to bias how left chooses to move using some function, maybe some extremely complicated neural network or something far simpler. Similarly, we could complicate matters by biasing which of left or right moved first on average. We'd start to get a different average over many plays of this game, right? sliding away from 1/2 closer and closer to 0. Yes, there are lots of ways to make games and how we play them more complicated. And truly, the infinite sky is the boundless limit. But we can definitively say something about those minimal, simplest constructions and implementations of systems possible. And that truly does help us. If you're into Bayesianness, these are our flattest priors. But flat and simple doesn't necessarily mean fair. Take -1, take +1. Does all of this mean we just take the average of the undominated options on either side of our composition to know its game value? No, not generally. It works like that for 1/2 because we're right at the bottom of our number tree, or top of our number window, however you like to orient it. But more than that, it works for 1/2 because one of the players can move to 0 on their next turn. You'll find this pattern continues on, and it's a very exciting pattern we'll see in other non-numeric contexts. But trying different patterns to see for yourself, you'll find the canonical value of a game is the simplest number between the sides as options, which is not necessarily the average, and certainly not defined by the average. For example, look at this hack-and-bush game, and what the two sets of options are. Two variations on the number 1/2 for left, and the number 2 for right. Clearly this is a positive game that left will win, but what is it worth to left compared to any other? Say if it's in a compound with other games, and so play choices exist beyond this funny little guy. If we'd take the average of the sides, we'd figure this game was about 1 1/4. But playing it out, we see the simplicity property in action, that this game's value is actually 1, which is the strictly simplest number between 1/2 and 2. Indeed, left was always ahead by one simple move. This becomes all the more clear as we sum this game with others to find those balanced 0 positions. We see 2 copies of this game are balanced by -2 to make it a second player win. Also, a fascinating aspect of surreal construction is how the same numbers are born over and over again, reinforcing the patterns that created them. So which is the simplest construction of all of these reconstructions? It turns out the birthdays help us with the simplicity concept, where the simplest number between 2 others is also the earliest born. It turns out we can't completely escape time with math. You'll see more and more what I'm talking about. There's a bit more to show you and what these simplest aspects of games do for us. Like, why don't we just study graphs instead of bringing in these relatively funny assumptions of a game? That is where we'll pick up in the next installment of this Surreal Primer. And now an important postscript. If you want a great comprehensive overview of combinatorial games, then check out the video by Owen Maitzen, linked in the description. I discovered his video after getting well underway on this primer material and was very relieved someone had done as practically perfect of an overview on general combinatorial games as really anything can be in this world. This will allow us to focus on the primer material particularly geared to the Surreal Physics storyline. Note we are exploring the relaxation of certain default assumptions of games here, including some that Owen lists, to bring what they have to teach us to quantum spacetime, as well as qualia and the math of mind more generally, something games I believe will help us connect in time. After all, physics is the study of observable relationships, and we can't stay focused on the most predictable ones forever. Games indeed gives us some hints as to why the smallest observables are indeed the most predictable, but only to a point. I'll say I was going to reach out to Owen to see if he was working on anything else related, as he warned he may not, and so I was pretty devastated to find out he is no longer with us. From what I can tell, by all accounts, Owen was a genius we lost well before his time. To everyone still listening, please take care of yourselves, and enjoy his wonderful video and also his outstanding music on his linked channel. Also, Elwyn Berlekamp, a father of combinatorial games, has a delightful YouTube channel, also linked. Berlekamp, like John Conway and Richard Guy, who we have to thank for the Winning Ways volumes and so much more, are each no longer with us since just 2019 or 2020. We lost Owen even more recently. But their ideas are alive and well, and their legacies will live on, I have no doubt.